Okay, good afternoon, students. Let's start today's discussion. In the last lecture, we have discussed the voltage divider biasing of BGT, and it was left as a homework assignment kind of thing for you to look at how we can do the analysis of a voltage feedback DC biasing. So I hope that most of you may have been done with this, but quickly let us look at how we can uh, analyze this kind of particular circuit. So under the fourth uh, configuration which was left for you is this one. So voltage stabilizer, so this emitter stabilizer resistance is mostly used because this reflects back at input by beta plus 1 times. Okay, so it just increases the input resistance. Okay, that's why it is mostly used. RE is mostly used. So say this is RC, RB, and BCC applied here. So in this configuration, again, already we have seen that we can just see what are the currents flowing through these. Let us say this is the collector here of this transistor, base, and emitter. Suppose the current through the emitter is say IE here, and the current into the base is say IB, and into the collector is say IC here. This current which is flowing through RC in that case becomes a different one as compared to the IC. Let us say that this is IC dash, and if we want to write the equation for the IC dash, then it will be IC plus IB here. Okay. So IC plus IB is nothing but IE. So we can also say that the current flowing through this RC is nothing but IE. So this is the current flowing through this IE. Now we can again say that there are uh, two loops, one including the input side, one including the output side. So let us disclose this. So we can say that this is the circuit here, biasing circuit, and here we apply the BCC. So this is nothing but BCC exaggerated. So we have now one loop consisting of this one, and another loop we can see is at the output side here. This is the second loop. So loop one should understand that here it is ground and here it is ground, so both can be thought of connected together like this ground. Okay, we can assume that this is a common ground here. In that way we can just figure it out that indeed it is a loop here. So one by one we can take the input loop or output loop. So suppose we intend to look at the first input loop here. So for this purpose, again let us redraw this circuit quickly. This is for illustration purpose only, need not to redraw. So base, collector, emitter. So voltage drop across a base emitter is BBE. Now we can apply this KBL into this loop, which we see. This is the loop in which we intend to apply the KBL loop. So current through RC, we have seen it is IE. Current through RB happens to be the current which is going into the base, that is IB. And again, RE, okay, through this RE, the current IE is going to flow. Okay. So now we can write the KVL expression for this. So KVL expression can be written like this here: minus BCC plus IE RE RC. Okay, first voltage drop across RC, then voltage drop across RB is IB times RB, and then the voltage drop across base emitter is BBE, and voltage drop across RE is IE RE to be equal to 0. So in this way, we can write the KVL equation for the input loop here. Now we can rewrite this equation by exploiting that IE is equal to IB plus IC, and IC is beta times IB, so it is nothing but 1 plus beta times IB. So we can take the advantage of this and find out the current IB. So this can be written as, after substitution here, let us take common IB from these terms here. So we have 3 terms over here, in which IB seems to be common. So first is 1 plus beta times RC, and the same thing will be with RE also. So we can club these together and write RC plus RE plus RB to be equal to BCC. Voltage terms, let us put it on the right side. BCC minus BBE. Now from here, we can write this value of IB to be equal to BCC minus BBE divided by 1 plus beta times RC plus RE RB. So we can see that this confusion seems to be very good in terms of that it is reflecting at the input a resistance B1 plus beta times RC plus RE, whereas in the emitter stabilized biasing cases we see that it was only RE reflected beta times at the input. So in that way, it is increasing the input resistance too large, okay, together. So IB in this way, we can find it out. The nominal values for the silicon transistor is say BB may be taken as 0.7 volt or so, and other values like parameters related to the transistor like beta. Beta may be given in the problem. Okay, and circuit parameters RC, RE may be given to us, and we need to find out IB. Okay, once we found the value of IB, we can find the IC, we can find the IE also. So all these currents are known to us as soon as we find the value of IB. Now we can find out parameters at the related to the output loop of this configuration here. So for that, again, let us redraw this circuit quickly. RC, RE, and again voltage source VCC. Now in this case, we want to apply this KBL through this output loop, in which we have a voltage drop across collector emitter terminal of this transistor, given by BCE here. Again, the current IE is going to flow through RC and RE both, and we can write the KBL into this loop now. So it will be minus BCC plus IE RC plus RE. We can write it together because the same current is flowing through RC and RE, plus BCE to be equal to 0. So now from here BCE can be found easily. BCE will be equal to BCC minus IE. IE can be written in terms of IB as 1 plus beta times IB into RC plus RE. So in this way, BCE can be found. Once we know this BCE value, we can find out the BC by adding BC into the emitter voltage BE, and BE can be found by just multiplying this IE times RE. This is the voltage drop occurring across emitter resistance RE. Once we know all these here, the base voltage also can be found by adding BBE into emitter voltage B. So all these values we can easily found, and so the operating point we can decide that our transistor. Okay, so in this way we can do our analysis. So for example, here we have, say, a circuit, biasing circuit given like this here. With values here, let us say this is 250 kilo ohms with a BCC 10 volts. RC is say 4.7 kilo ohms. And RE is say 1.2 kilo ohms. Okay, so find out the operating point collector current and collector emitter voltage. So this is the biasing circuit given here. Apart from this, sometimes these parts also may be given with V0 and Vi. But we don't really need to take into account this, because for DC, these capacitors are going to act like open circuit. Okay, so no need to worry about the presence of these coupling capacitors for DC analysis. So we can directly use these equations which we have derived here. One more thing is given for this transistor, beta is equal to 90. So for calculations, one need to use this beta value here. So one can do, you people might try to do this problem and find out the values ICQ and BCEQ. There's some variations of these transistor circuits may also be given, biasing circuits may also be given, and we may also proceed in a general way as we have done earlier, by applying carefully the KCL and KVL and do our analysis. Care, because we need to look at, even though there is a single loop, we may have different values of the current flowing through the base and emitter and collector. Okay, that's why we have to be careful in the analysis of such transistor circuits. So that's only the difference here. For an example here, let us look at this circuit here. Suppose we have a transistor at emitter here. Instead of grounding it, one is applying a voltage minus 9 volt, and RC is 1.2 kilo ohms, say, and this is grounded instead, and one needs to suppose this is also given here, and at base we are given a resistance 100 kilo ohms. So for this circuit, let us find the different values of the voltages. So find, let us say that BB and BC, and current also we can find out of it. Let us say we need to find out the current also. So how to proceed here for such a circuit? So in this circuit here, again, as illustrated, that this part may not be taken into account because we are doing the DC analysis. Okay, so only the central part of the circuit we do have. Now we can see that at input loop here, we have a 100 kilo ohm resistance, and this is base emitter. Okay, and let us say that this is collected here. Before proceeding here, let us see that this is an NPN transistor here, and now if we look at this part here, including base emitter junction, okay. So if we look at this base emitter junction, means base is here, emitter is here, resistance is there, something like this, and here we have a voltage source like this, -9 volt at emitter. This side is P type and this is N type. Let us see that even though we have applied a negative voltage at emitter, but if we look at in this loop, okay, if we look into this loop here, then we shall see that the positive polarity of this battery is connected to the base. So base emitter junction is going to be forward bias. Okay, even in this case, this base emitter junction is forward bias and it will be on. Okay, so we can do it. We can apply KVL into this emitter loop here, sorry, input loop here, as shown over here, marking the currents. So let us see what currents are going to flow through this 100K resistance. It is nothing but the base current IB. IB is flowing. Okay, so let me rewrite clearly. Okay, so in this loop here we have ground. So this into this part, it is the base current IB which is going to flow, and 9 volt. Okay, there is no need of writing -9 because we have just put it a proper battery polarity at the emitter side. Okay, to just show that it is really -9 volt. Okay, so we can write like this here. Base emitter junction is over here. Let us again say that between base and emitter, a VBE voltage is going to drop when it is forward biased. So VBE voltage for say this case here is say 0.7 volt. If we are given that this is a silicon transistor, then for silicon transistors this is going to be 0.7 volt. And also let us say that beta of this transistor is required to be known. Let us say that it is 45, for example. Now after this we can write the KVL equation here. So let us say that this is the current flowing here. So voltage drop is with this polarity here. Now we can apply the KVL into this loop. So IB times RB plus BBE minus 9 is equal to 0. Okay, this will be the KVL for this loop. If we assume that RB is the resistance here, BB is the voltage drop across the base emitter junction, and this 9 volt source is here. So from here, IB current can easily be found as 9 minus BB, that is 0.7 volt, divided by RB. RB is given here 100K. Okay, so in this way we can write. So 8.3 into 10 power minus 5 amperes. So this can be written as 83 microamperes. So IB is found in this way, and as soon as we know the IB value, we can take the help of this beta value here and write the value for the IC current, assuming that this is in active region. So 45 times 83 microampere. This one can find it out. IE also one can find it out. Okay, IE can also be found. Sorry, I think that I lost connection for a while. Can anyone confirm whether my screen is being shared or not?
Yes, sir, it is shared.
Okay. Okay, so we were here that we can compute the value of IC in this way with the knowledge of the base current IB. And once we know this value, we can find out other values also, like BCE, by applying the KVL into the output loop. So let us do this also. So let me redraw this circuit here. So we can put the 9-volt battery here at the emitter with this its polarity -9, okay, minus polarity facing at the emitter side. So collector emitter. Let us say that voltage drop across collector emitter is BCE and RC is here given as 1.2 kilo ohms. We don't need to draw
Hello, sir.
the, yes.
Sir, your screen got struck. Sir, can you please again reshare?
Okay, so that's what I was trying to make sure. Share. Now it is changing or not?
No, sir.
No, no changing. There was some interruption in the network, and because of that, connection was Hmm. Hello, dear students. Actually, I am facing some problem in connecting back with the tablet. Okay, so we shall stop here. We will meet tomorrow. Thank you. You people may leave now meeting.
Okay, thank you, sir.
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 Okay, thanks all.